Welcome to CO556 Network Systems. This is week 4, and this week we're looking at chapter 5 of the Cisco syllabus, which is STP concepts. STP stands for Spanning Tree Protocol Concepts. So the module objectives for this week are to obviously look at Spanning Tree Protocol, explain how the Spanning Tree Protocol enables redundancy in a layer 2 network. We'll look at the purpose of Spanning Tree Protocol and explain common problems in a redundant layer 2 switch network. Look at operations and explain how Spanning Tree Protocol operates in a simple switch network. And we'll look at the evolution of Spanning Tree Protocol and explain how rapid PVST Plus operates. So the purpose of Spanning Tree Protocol. So redundancy in layer 2 switch networks. So this topic covers the causes of loops in a layer 2 network and briefly explains how Spanning Tree Protocol works. Redundancy is an important part of the hierarchical design for eliminating single points of failure and preventing disruption of network services to users. Redundant networks require the addition of physical paths, but logical redundancy must also be part of the design. Having alternate physical paths for data to traverse the network makes it possible for users to access network resources despite path disruption. However, redundant paths in a switched Ethernet network may cause both physical and logical layer 2 loops. Ethernet LANs require a loop-free topology with a single path between any two devices. A loop in an Ethernet LAN can cause continued propagation of Ethernet frames until a link is disrupted and breaks the loop. So, in a nutshell, this describes what Spanning Tree Protocol is there for. It is there to stop loops occurring. You don't want loops within your network because, as it says, it will continue to propagate network traffic around those loops, which can essentially grind the network to a halt. So if you get broadcast traffic especially, that would be propagated again and again and again, broadcasting. We call this a broadcast storm, and the trouble is all those frames and packets of information that are being sent around the network just simply build up until eventually the whole network grinds to a halt because it is just carrying the broadcast traffic and nothing else can get through. So this is really bad thing within networks to have these loops, so we don't allow them. And we use the Spanning Tree Protocol to ensure that they don't occur. That's really at the heart of it. So the Spanning Tree Protocol. So Spanning Tree Protocol, or STP, is a loop prevention network protocol that allows for redundancy while creating a loop-free layer 2 topology. So you want redundancy within your network. It's really important that you can have multiple pathways through your data network, so that if one of your devices breaks or if a link goes down, then you still have a backup option. You still have other pathways that can be relied upon to keep the data moving. So in a network system, especially in enterprise systems, you don't want single points of failure. You want to have multiple pathways. The trouble with multiple pathways is if you left them unregulated and you had no way of actually containing or taking out those loops that would occur at a logical level, then you've got the potential of loops occurring and broadcast traffic building up and clogging your network, which would be just as bad as not having any, or worse, in fact, not having the loops there or having the redundancy there. So STP, Spanning Tree Protocol, logically blocks physical loops in a layer 2 network, preventing frames from circulating the network forever. So in the diagram that we see here, you can see that trunk 2 has been blocked because it would create a link between S2, S3 and S1. So traffic could go around and around from S1 to S2 to S3 again and again and again. So if you've got a broadcast onto this network, S2 could broadcast that out to S1, S3, and then they would broadcast out, and it would just continually broadcast out around and around forever until all that traffic built up and blocked the network. So by logically blocking the link, trunk 2 link between S3 and S2, you've effectively cut off that loop. And the Spanning Tree Protocol looks for loops like that and cuts them off automatically by blocking the ports at the ends, based on obviously rules and protocol rules that it observes. So spanning tree protocol recalculation. So spanning tree compensates for a failure in the network by recalculating and opening up previously blocked network ports. So essentially, that trunk 2 port was blocked automatically. But if trunk 1 went down, then what spanning tree protocol would do is unblock it. So it would take the block off of trunk 2 in order to compensate automatically for the failure in trunk 1. So it still means communications could then go between S2, S3 and S1, but they would be doing it via trunk 2 rather than trunk 1 in our diagram. Similarly, if trunk 1 was then brought back online, it would then block off trunk 2 again automatically to ensure traffic is going through the trunk 1 link S1, S2, S3. So it automatically adjusts based on the need within the network, but still maintaining loop-free communications. So issues with redundant switch links. So path redundancy provides multiple network services by eliminating the possibility of a single point of failure. When multiple paths exist between 2 devices on an Ethernet network, there is no spanning tree implementation on the switches. A layer 2 occurs. So if you don't have spanning tree running on a layer 2 switch, then you're going to get a loop essentially if you've got multiple pathways. A layer 2 loop can result in a MAC address table instability, link saturation, and high CPU utilization on switches and end devices, resulting in the network becoming unusable. Okay, so the MAC address table instability, that's caused because every time you get new traffic coming in, it's going to be relearning the MAC addresses for that traffic. So over time, the MAC address table will simply add in new MAC address details for every entry it makes, and that will essentially use up the MAC address table and just until there's no other routes available in there essentially. And in terms of link saturation, then obviously all the traffic is going over those links, and just because it's a high CPU, because the devices will be continually processing this broadcast traffic and the broadcast time that ensues. So layer 2 Ethernet does not include a mechanism to recognize and eliminate endlessly looping frames. Both IP version 4 and IP version 6 include a mechanism that limits the number of times a layer 3 networking device can retransmit a packet. A router will decrement the TTL, or time to live, in every IP version 4 packet and the hop limit field in every IP version 6 packet. When these fields are decremented to 0, a router will drop the packet. Ethernet and Ethernet switches have no comparable mechanism for limiting the number of times a switch retransmits a layer 2 frame. Spanning tree protocol was developed specifically as a loop prevention mechanism for layer 2 Ethernet. So essentially, routers will drop packets. They will drop them after so many times, and they have their time to live counter for that exact purpose. But in frames, we have nothing. In layer 2 devices, they have nothing to recognize that they have propagated this frame many times before, and they just keep going and going and going. So spanning tree protocol has to be part of the network suite, because it has to do that job. It has to clear out the potential for these loops to occur. So layer 2 loops. Without the spanning tree protocol enabled, layer 2 loops can form. They will cause broadcast, multicast, and unknown unicast frames to loop endlessly. This can bring down network pretty quickly. Very quickly, in fact. When a loop occurs, the MAC address table on a switch will constantly change with the updates from the broadcast frames, which results in MAC address or MAC database instability. This can cause high CPU utilization, which makes the switch unable to forward the frames. An unknown unicast frame is when the switch does not have the destination MAC address in its MAC address table and must forward the frame out of all ports except the ingress port. So as you get more instability within your MAC address table on the switch, it will then cause unicast frames to not know where they need to go, and no destination, and they will continue to propagate as well. So this broadcast storm continues to propagate more and more frames of this nature, and until the network grinds to a halt. So a broadcast storm. So a broadcast storm is an abnormally high number of broadcasts overwhelming the network during a specific amount of time. Broadcast storms can disable a network within seconds by overwhelming switches and end devices. Broadcast storms can be caused by hardware problems such as a faulty network interface card or from a layer 2 loop in the network. Layer 2 broadcasts in a network, such as ARP, Address Resolution Protocol requests, are very common. Layer 2 multicasts are typically forwarded the same way as a broadcast by the switch. IPv6 packets are never forwarded as Layer 2 broadcast. ICMPv6 neighbor discovery uses Layer 2 multicasts. A host caught in a Layer 2 loop is not accessible to other hosts on the network. Additionally, due to the constant changes in its MAC address table, the switch does not know out of which port to forward unicast frames. To prevent these issues from occurring in a redundant network, some type of spanning tree protocol must be enabled on the switches. Spanning tree is enabled by default on Cisco switches to prevent Layer 2 loops from occurring. So if you run a networking packet tracer and you go into the simulation mode and you just click through the forward button in that sort of suspended time mode, you'll see after a while STP frames start to actually pop up, and we can see the spanning tree protocol enabled by default is at work in the network. So it's just worth having a look at that. So just a simple network, and have a look at the spanning tree protocols that are coming out and they're being propagated every now and then. And they're there to keep track of whether there's a loop forming in the network and to actually block ports if they find one. So you have to continually be checking the network. You have to have these spanning tree protocols running in order to check the network constantly. So there is a certain amount of overhead with spanning tree protocol in that it's propagating its own protocol frames in order to check the network. So it is possible to turn spanning tree protocol off if you want to save a little bit of bandwidth for the spanning tree protocol running, but if you're going to do that, you have to be very, very assured that you don't have any loops within your network. But when you run redundancy, you normally do have, and it's very, very important to have spanning tree protocol running anyway, because it will need to automatically adjust if one of your links goes down and you move to the other. So there's not really a reason to turn it off, but at the same time it is possible, but you're probably a bit unwise to do that. So the spanning tree algorithm. So spanning tree protocol is based on an algorithm invented by Radia Perlman while working for Digital Equipment Corporation, that's DEC, and published in the 1985 paper, An Algorithm for Distributed Computation of a Spanning Tree in Extended LAN. If I can find that paper, I'll actually make a link to it. I think I have it somewhere in the Blackboard. So a spanning tree algorithm, STA, creates a loop-free topology by selecting a single root bridge, where all the other switches determine a single least cost path. STP prevents loops from occurring by configuring a loop-free path through the network using strategically placed blocking state ports. The switches running STP are able to compensate for failures by dynamically unblocking the previously blocked ports and permitting traffic to traverse the alternate pathways. So how does the spanning tree algorithm create a loop-free topology then? Selecting a root bridge. This bridge, which is a switch, is the reference point for the entire network to build a spanning tree around. So essentially we're deciding on which switch is going to be the root bridge when you implement spanning tree within a network infrastructure. Blocking redundant paths. Spanning tree protocol ensures that there is only one logical path between all destinations on the network by intentionally blocking redundant paths that could cause a loop. When a port is blocked, user data is prevented from entering or leaving that port. Now, this is a very key process that STP does by blocking a particular pathway and unblocking it. It allows for the access to that particular port to the network, and hence it controls the pathways that are allowed within that network. So create a loop-free topology. So a blocked port has the effect of making that link a non-forwarding link between two switches. This creates a topology where each switch only has a single path to the root bridge, similar to branches on a tree that connect to the root of the tree. Okay, so we speak of spanning tree protocol. There's only one root bridge at the base of the tree, and everything only has one pathway to that particular switch, to that particular route. Recalculating in case of link failure. The physical paths still exist to provide redundancy, but these paths are disabled to prevent the loops from occurring. Okay, so there are redundant paths, there are loop paths essentially in the network, but because they are disabled on a particular point or particular port within that loop, they won't occur, or loops won't occur within the network. If the path is ever needed to compensate for a network cable or switch failure, STP then recalculates the paths and unblocks the necessary ports to allow the redundant path to become active. STP recalculations can also occur anytime a new switch or a new inter-switch link is added to the network. So this is really the beauty of spanning tree protocol in this recalculation that it's able to do on a regular basis. If you change something within your network topology, so if you take out a switch or put a new switch in or add switches to your network, then spanning tree protocol will automatically realign itself for that new addition. Similarly, if a link goes down, as I've said, then it will again recalculate, reassess, and adjust for that that path going down and bring in to play one of the redundant links. So we have a little packet tracer exercise. Again, investigate spanning tree protocol loop prevention. So again, this is a useful exercise to do. It gets you to create and configure a simple free switch network with spanning tree protocol, view the spanning tree protocol operation, and disable spanning tree protocol and view the operation again. So basically it just shows you what happens if you turn the spanning tree protocol off after understanding how it's in operation, and you'll see the network essentially grind to a halt with that. So it's useful just to kind of see that, obviously in the lovely packet tracer simulation rather than on a real production network. So spanning tree protocol operations then. So the steps to a loop-free topology. So using the spanning tree algorithm, spanning tree protocol builds a loop-free topology in 4-step process. Step 1, it elects a root bridge. In step 2, it elects root ports. In step 3, it elects designated ports. And in step 4, it elects alternate blocked ports. So during the spanning tree algorithm and spanning tree protocol functions, switches use protocol data units or bridge protocol data units. These are BPDUs to share information about themselves and their connections. BPDUs are used to elect the root bridge, root ports, designated ports, and alternate ports. So the bridge protocol data units, these BPDUs, are essential to the functioning of the spanning tree protocol. This is the way that the switches will share information relating to spanning tree amongst themselves. So all 4 of those steps that the spanning tree protocol needs to, and the spanning tree algorithm needs to run, have to be delivered between switches via these BPDUs. So each BPDU contains a bridge ID that identifies which switch was sent the BPDU. So every BPDU will have this bridge ID in it identifying the switch that was sent the BPDU. The bridge ID is involved in making many of the spanning tree algorithm decisions, including root bridge and port roles. The bridge ID contains a priority value. The MAC address of the switch and an extended system ID become part of this bridge ID. The lowest bridge ID value is determined by the combination of these three fields. So a priority value, the MAC address of the switch, and an extended system ID are what's determined the bridge ID value, and that's the combination that's used. So the bridge priority, the default priority value for all Cisco switches is the decimal value of 32,768. The range is 0 to 61,440 in increments of 4,096. So a lower bridge priority is preferable. A bridge priority of 0 takes precedence over all other bridge priorities. So in order to determine the bridge, it's the one with the lowest priority that we're essentially looking for. The extended system ID is a value, is a decimal value added to the bridge priority value in the bridge identity. So to identify the VLAN for this particular BPDU. The MAC address, when two switches are configured with the same priority and have the same extended system ID, the switch having the MAC address with the lowest value expressed in hexadecimal will have the lower bridge ID. Okay, so we're trying to determine between switches the one with the lowest bridge ID, and we're using the combination of these three different things: bridge priority, extended system ID, and MAC address to do that. And the MAC address, of course, being as that's unique for each device, is essentially there to break any deadlock. So if they have the same bridge priority and extended system ID, then you can break the deadlock with the MAC address. So in step 1, it's about electing the root bridge. So the spanning tree algorithm designates a single switch as the root bridge and uses it as a reference point for all path calculations. Switches exchange BPDUs to bridge protocol data units to build the loop-free topology, beginning with selecting the root bridge. All switches in the broadcast domain participate in the election process. After a switch boots, it begins to send out BPDU frames every 2 seconds. These bridge protocol data unit frames contain the bridge ID of the sending switch and the bridge ID of the root bridge, known as the root ID. A switch with the lowest bridge ID will become the root bridge. At first, all switches declare themselves as the root bridge with their own bridge ID set as the root ID. Eventually, the switches learn through the exchange of BPDUs which has the lowest bridge ID and will agree on one root bridge. So that's a really important point. So they all think their bridge, they all think their root bridges to start with, and they will exchange on that basis. It's only over a certain amount of time, when they exchange the bridge protocol data units and build up information amongst themselves about the spanning tree for the spanning tree algorithm, that they start to determine who really is the root bridge. And the root bridge is the device with the lowest bridge ID. So the one with the lowest ID will become the root bridge. And in the diagram that you can see here, we have 3 switches, S2, S1 and S3, and you can see that essentially S1 has become the root bridge because it has the lowest number. So it has the lowest priority of all those devices. So it actually has a higher MAC address, but the priority number is lower. So the other two are 32,769 and it's 24,577. So on that basis, that one is actually the lower bridge ID. So that becomes the root bridge. So the impact of default bridge IDs, because the default bridge ID is 32,768, it is possible for 2 or more switches to have the same priority. In this scenario, where the priorities are the same, the switch with the lowest MAC address will become the root bridge. The administrator should configure the desired root bridge switch with a lower priority. Yeah, so you can control basically which device you want to become the root bridge as an administrator by simply lowering the priority away from the 32,768 number. The reason it says 32,769, by the way, is because there's another ID that's added as well, the bridge ID, which is normally it gives it a sort of priority of 1 on there, so it increases the number. It's normally the default for the VLAN. Oh, see, we're saying that at the bottom. So no, that's the difference. Not a mistake in the slides. They are 32,769, but the default is 32,768, and it's the VLAN assignment that's added to it. But we'll come back. And the default, of course, is 1. Anyway, so you can control the priority, and you should lower it for the one you want to be the root bridge. So although they work things out for themselves, as an administrator, obviously you can maintain control and you can set things up. So in the figure, all switches are configured with the same priority of 32,769. Here the MAC address becomes the deciding factor as to which switch becomes the root bridge. The switch with the lowest hexadecimal MAC address value is the preferred root bridge. In this example, S2 has the lowest value for the MAC address and is elected as root bridge for the spanning tree instance. But of course, we've changed the priority of one of those. So S1, we changed the priority to 24,577 on the priority, and then that becomes the root bridge. So note the priority of all the switches is 32,769. The value is based on 32,768 default bridge priority, and the extended system ID, which comes from the VLAN assignment associated with each switch. So VLAN 1 gets added to that priority number. So determining the root path cost. So when the root bridge has elected or has been elected for a given spanning tree instance, the spanning tree algorithm starts determining the best paths to the root bridge from all destinations in the broadcast domain. The path information, known as the internal root path cost, is determined by the sum of all the individual port costs along the path from the switch to the root bridge. When a switch receives the BPDU, Bridge Protocol Data Unit, it adds the ingress port cost of the segment to determine its internal root path cost. The default port costs are defined by the speed at which the port operates. So the table below shows the default port cost suggested by the IEEE. Cisco switches by default use the values as defined by the IEEE 802.1d standard, also known as the short path cost for both spanning tree protocol and the rapid spanning tree protocol. Although switch ports have a default port cost associated with them, the port cost is configurable. The ability to configure individual port costs gives the administrator the flexibility to manually control the spanning tree paths to the root bridge. Now that's again another key point. So you're learning this because you want a network administrator. So a network administrator can change the priority of the switches to make them into the one that they want to be the root bridge, can become the root bridge, and you can also adjust this calculation on the costs. So you can adjust how the algorithm essentially builds up its path. So the spanning tree protocol paths are created based on this cost, and you can alter those costings. But by default, we have this. It's based on the speed of the link. So a port that's a 10 megabit per second port would be a cost of 100. A 10 gigabit per second link would be a cost of 2, and you can see that the cost essentially reduces the faster the link speed. So, and in rapid spanning tree, it's similar in that we have this reduction from 2 million down to 2,000 on the speed of the link, but with obviously higher numbers are used. But it's just a way of actually determining a metric value, a cost, based on the speed of that link. So the speed of the links are important, because if you think about it, if you have a loop in your network, you have redundancy in your network built in, you might have redundant pathways which are on slower connections. So they might be slower links. They might be, they're only there for backup. They're only there if things have gone wrong in the main fast link. So you want to utilize your fastest links for your day-to-day data transference. You want to have the network running as fast as possible. That's always the case. But you might have some slower links that would be fine for redundancy, for backup, so that if you need to keep the network running, you can go to them. We just don't want to use them all the time. So the spanning tree protocol needs some way to actually identify the difference between a fast route and a slower route. So this costing metric that it utilize based on the speed of those links is just a good way of trying to determine not only which path to block, which paths to use, but basing that on the actual speed. So we always identify the fastest link possible. So in step 2, we were electing the route port. So after the route bridge has been determined, the spanning tree algorithm is used to select the route port. Every non-route switch will select one route port. The route port is the port closest to the route bridge in terms of overall cost to that route bridge. This overall cost is known as the internal route path cost. The internal route path cost is equal to the sum of all the port consistent costs along the path to the route bridge, as shown in the figure here. So in our figure, we still have our route bridge in S1, and we have various paths to it. So in terms of determining route ports towards route bridge, we can then identify the route ports which are quickest. So from S2 to S1, that's essentially a path 1 costings. So that would be a cost of 19, and there is only one link there. So effectively, we have a cost of that particular route, that path 1, if you like, as being 19. If we go the other way, we have a secondary path to S1 from S2, but the trouble is that requires the traffic to go across 2 links. So it's 19 times 2 in the costings, which gives it a metric of 38. So the 38 path is not obviously desirable. The lower the cost, the faster it is. So the 19 cost link, that has to be the route port. So the route port for S2 has to be fast Ethernet 01, because that's heading towards the route bridge, and that link between it and the route bridge is the quickest path. It's the fastest, and determined by the metric, which gives it the lower cost. And you can see for S3 going towards the route bridge, again, what's the quickest path from S3 to the route bridge? Well, that's again fast Ethernet 0 on it, so that's its route port. So paths with the lowest cost become preferred, and all other redundant paths are blocked. In the example, the internal route path cost from S2 to the route bridge S1 over path 1 is 19, while the internal route path cost over path 2 is 38, because path 1 was the lower. Overall path cost to the route bridge, it is the preferred path, and fast Ethernet 01 becomes the route port on S2. So the first step is electing designated ports. So every segment between 2 switches will have one designated port. So the designated port is a port on the segment that has the internal route path cost to the route bridge. In other words, the designated port has the best path to receive traffic leading to the route bridge. So this is receiving traffic onto that particular device. So what is not a route port or designated port becomes an alternate or blocked port. All ports on the route bridge are designated ports. If one end of a segment is a route port, the other end is a designated port. All ports attached to end devices are designated ports. On segments between 2 switches where neither of the switches is a route bridge, the port on the switch with the least cost path to the route bridge is also a designated port. So we can see here in our diagram designated ports on the root bridge are all the ports on that root bridge, so fast Ethernet 2 and fast Ethernet 3. On switch 2, we have a designated port of fast Ethernet 2 because that's a port in going towards the root port out of fast Ethernet 1. Step 4 then is electing alternate blocked ports. So if a port is not a root port or a designated port, then it becomes an alternate or backup port. Alternate ports are in discarding or blocking state to prevent loops. So in our figure, the Spanning Tree algorithm has configured port fast Ethernet 2 on S3 in the alternate role. Port fast Ethernet 2 on S3 is in the blocking state and will not forward. Ethernet frames, all other interswitch ports are in forwarding state. This is the leap prevention part of Spanning Tree protocol. So the alternate port then had to be fast Ethernet 2 on S3 because that was the only port kind of left that wasn't a designated port within the loop. So by default it becomes blocked. So in this case it's blocked to prevent any Ethernet frames going on. So you couldn't send to that port data, it would just be dropped at that particular port. It's blocked essentially at this particular point. So elect a root port from multiple equal cost paths. So when a switch has multiple equal cost paths to the root bridge, the switch will determine a port using the following criteria. So the lowest sender bridge ID, the lowest sender port priority, or the lowest sender port ID. So we have to have some ways of essentially breaking deadlocks, and these criteria enable that to occur. So if you do get a deadlock within a system, which might happen, then we can use these metrics to actually break that lock. So elect a root port from a multiple equal cost paths. So the lowest sender bridge ID. So in this topology you have 4 switches with switch 1 as the root bridge, port fast Ethernet 1 on switch 3 and port fast Ethernet 3 on switch 4 have been selected as root ports because they have the root path cost to the root bridge for their respective switches. S2 has 2 ports, fast Ethernet 1 and fast Ethernet 2, with equal cost paths to the root bridge. The bridge IDs of S3 and S4 will be used to essentially break the tie. This is known as the sender's bridge ID. S3 has a bridge ID of 32,769.5555555555555, and S4 has a bridge ID of 32,769.111111111111. Because S4 has the lower bridge ID, the fast Ethernet 1 port of S2, which is the port connected to S4, will become the root port. So in a way, looking at this, it's kind of a situation that perhaps wouldn't necessarily occur very readily within a production network, but it's just being used to illustrate exactly how this protocol works out and determines if you have this sort of tie. By seeing a tie like this in a sort of artificially contrived situation, you can start to see how the Spanning Tree protocol works out which ports are root and which ports are designated based on those metrics. So elect a root port from a multi-cost path. So again, lowest sender port priority. So this topology has 2 switches which are connected with 2 equal cost paths between them. S1 is the root bridge, so both of its ports are designated ports. S4 has 2 ports with equal cost paths to the root bridge. Because both ports are connected to the same switch, the sender's bridge ID S1 is equal. So the first step is essentially a tie. Next is the sender's port priority. The default port priority is 128. So both ports on S1 have the same priority, which is also a tie. However, if either port on S1 was configured with a lower port priority, S4 would put its adjacent port in forwarding state. The other port on S4 would be in blocking state. Lowest sender port ID. The last tiebreaker is the lowest sender's port ID. Switch 4 has received the bridge protocol data units from port Fast Ethernet 1 and port Fast Ethernet 2 on S1. The decision is based on the sender's port ID, not the receiver's port ID. Because the port ID of Fast Ethernet 1 on S1 is lower than the port Fast Ethernet 2, the port on Fast Ethernet 6 on switch S4 will be the root port. This is the port on S4 that is connected to the Fast Ethernet 1 port on S1. Port Fast Ethernet 5 on S4 will become an alternate port and be placed in a blocking state. So again, you need to think carefully about this example here and think through the process. So this is a little bit, when you first come to spanning tree protocol, this stuff can seem a little bit overwhelming, and because there's quite a little bit of thinking to do in terms of how the algorithm works. But bear in mind that with any protocol like this, any algorithm, it just takes decisions the same again and again and again. So once you know the rules, once you know the protocol steps, then it will be implemented again and again and again, exactly the same way. The key with this, understanding this algorithm, is really in the fact that as an administrator of the network, if you understand how it's determining things within itself, then you can manipulate that algorithm to give you network efficiencies. So out of the box, as it were, spanning tree protocol doesn't necessarily give you the most effective and efficient network. And the reason that is, although it is based around these costings which are to do with speed, for example, and you might think, oh, that's great. But again, if you don't get the root bridge correct in the first place, then you're not necessarily going to be utilizing the best speed and the best sort of main trunk out of the network or into the network. So you need to think carefully about which device you really want as your root bridge to start with. Also, what spanning tree doesn't know is what data's traveling over those links. And although you might have a slower link, the type of data that's moving across it might actually be fairly minimal anyway, and it would be better if it was using that particular pathway than say another, which might be faster but is carrying another types of traffic. So again, it's really important to kind of determine which pathways you want the data to take and which pathways you want for redundancy and so on by controlling this algorithm. So the algorithm is there to do the automatic kind of switching if things go wrong, but in terms of its setup and administration, you definitely want to kind of be able to understand it a little bit so that you can manipulate it and make it fine tune it so that it's working the best for you. That's really where network administrators earn their money, to be frank, is in the fine tuning of these type of algorithms, because out of the box it might work, it might hit the best the sweet spot, but normally it requires a little bit of adjustment from an administrator who kind of knows what they're doing. So spanning tree protocol timers and port states. So spanning tree protocol convergence requires 3 timers. So these are as follows. So we've got the hello timer. The hello timer is the interval between bridge protocol data units. So the default is 2 seconds, but can be modified. Again, this is modifications that a network administrator might make between 1 and 10 seconds. Forward delay timer. The forward delay is the time that is spent in the listening and learning state. So the default is 15 seconds, but can again be modified to forward and 30 seconds. The max age timer, the max age is the maximum length of time that a switch waits before attempting to change the spanning tree protocol topology. The default is 20 seconds, but can be modified between 6 and 40 seconds. So you need to note the default times can be changed on the root bridge, which dictates the values of these timers for the spanning tree protocol domain. So you change it on the root bridge, and that will determine all the rest of the timers for other things. So you don't have to change it on individual switches. You can just change it on the root, and it will then be running the same on every other device within that spanning tree domain. So spanning tree protocol facilitates the logical loop-free path through the broadcast domain. The spanning tree is determined through the information learned by the exchange of the bridge protocol data unit frames between the interconnected switches. If a switch port transitions directly from the blocking state to the forwarding state without information about the full topology during that transition, the port can temporarily create a data loop. For this reason, spanning tree protocol has 5 port states, 4 of which are operational port states as shown in this figure. The disabled state is considered non-operational. So we have the blocking state, so if no BPDU is received, and we have a max age of 20 seconds on that by default. We have the listening state, which is if there's a forward delay of about 15 seconds. We have learning, which has a forward delay of 15 seconds, and we have forwarding. We also have blocking in blocking state until spanning tree protocol determines if a port is not is a root or designated port. So that particularly makes that link come back up. So blocking is a disabled state, non-operational at that point. So operational details of each port state. So we've got a little simple table here that essentially summarizes the operational details of each port that we are looking at, and we can see the different states that are listed on the left-hand side. So we've got the blocking state, the listening state, the learning state, and the forwarding and disabled states. We can see the different states of the bridge protocol data units that are going to be here. So when it's blocking, it can only receive bridge protocol data units. If it's listening, it can receive and send. Learning and forwarding, it can also receive and send. If it's disabled, then it can't send or receive bridge protocol data units. In terms of the MAC address table, if it's in a blocking state, then there can be no updates to the table, and there can be also no way of forwarding data frames. If it's listening, again, it won't update the MAC address table and it won't forward any data frames. If it's learning, again, it won't forward any data frames, but it will update the MAC address table on the switch. That's true with forwarding as well. It'll make updates to the MAC address table, and of course it will actually forward some frames. When it's disabled, we get no updates, and we also get no forwarding. So these are the operational states that ports can be in at any one time. So per VLAN spanning tree, so spanning tree protocol can be configured to operate in an environment with multiple VLANs. In per VLAN spanning tree, which is PVST, abbreviated as, versions of the spanning tree protocol, there is a root bridge elected for each spanning tree instance. This makes it possible to have different root bridges for different sets of VLANs. A spanning tree protocol operates a separate instance of spanning tree protocol for each individual VLAN. If all ports on a switch are members of VLAN 1, then there is only one spanning tree instance. Yeah, so this is really important. So per VLAN spanning tree, we've been covering VLANs, we've looked at what VLANs are, and we've seen how important they are for dividing up our ports and dividing up our networks logically. Spanning tree protocol, because it's such an integral part of redundancy within networking, also will run per VLAN. So PVST versions of spanning tree protocol means that you can have your spanning tree protocol running with different VLANs, and it means it will then treat those switches differently depending on which VLAN it's operating within, which is really quite exciting. from the point of view of managing redundancy over multiple VLANs over multiple switches. So that's a really good thing. So let's have a look at the evolution of spanning tree protocol then. So there's been different versions of spanning tree protocol. Many professionals generically use spanning tree and spanning tree protocol to refer to the various implementations of spanning tree, such as rapid spanning tree protocol, RSTP, and multiple spanning tree protocol, MSTP. In order to communicate spanning tree concepts correctly, it is important to refer to the implementation or standard of spanning tree in context. Okay, so there are multiple versions of spanning tree protocol. So everyone just says it's a spanning tree protocol, but which version? You know, which instance of it? So rapid spanning tree protocol or multiple spanning tree protocol. There is differences between them, and it's kind of important you have that kind of context. So the latest IEEE documentation on spanning tree, which is the IEEE 802.1 D, which is 2004, says that spanning tree protocol has now been superseded by the rapid spanning tree protocol, RSTP. So the IEEE uses spanning tree protocol to refer to the original implementation of spanning tree and RSTP to describe the version of spanning tree specified in the latest standard, so 802.1 D 2004. Okay, so there is a difference. So if you hear someone saying spanning tree protocol, are they actually referring to the original spanning tree protocol, or are they referring to the rapid spanning tree protocol, the RSTP? So it's important to differentiate between the two. Because the two protocols share much of the same terminology and methods of the loop-free path, the primary focus in these materials is really on the current standard and the Cisco proprietary implementations of spanning tree protocol and rapid spanning tree protocol. So Cisco switch is running the Intel operating system 15 or later. They run PVST plus, which is by default. So that's per VLAN spanning tree plus, and that's their default. So this version incorporates many of the specifications of the IEEE 802.1D 2004, such as alternate ports in place of the former non-designated ports. We call them alternate ports rather than non-designated in PVST plus. And switches must be explicitly configured for rapid spanning tree mode in order to run the RSTP, the rapid spanning tree protocol. Okay, so they run spanning tree protocol, but they run the original version, and they talk about alternate ports rather than non-designated ports. So there's a little bit of language terminology and how they say. So if you want to run the rapid spanning tree mode, you have to turn that on. So different versions of spanning tree protocol then. So let's just have a look. So the original was spanning tree protocol. So the original 802.1 D version from the IEEE, which essentially is 1998 and sort of earlier, provides a loop-free topology in the network and redundant links, also called common spanning tree, just to make things even more slightly confused, I suppose. Have another acronym, CST, if you want. It assumes one spanning tree instance in the entire bridge network, regardless of the number of VLANs. So the original spanning tree didn't allow for per VLAN. So if it was regardless of how many VLANs you might have, you only have one spanning tree basically. So per VLAN spanning tree, PSVT, ST plus, that's a Cisco enhancement basically of STP that provides a separate 802.1D spanning tree instance for each VLAN configured in the network. PVST plus supports port fast, uplink fast, backbone fast, BPDU guard, BPDU filter, root guard, and loop guard. Okay, so this is how Cisco have kind of made their money, to be honest, in being one of the top network device and protocol providers. So they enhance the spanning tree protocol to add in all this extra security stuff, and also to make it per VLAN, which was a real leap forward. So 802.1D 2004 is the updated version of the spanning tree protocol, which incorporates IEEE's 802.1 W standard within it. You don't need to know too much about that. I mean, you can go and look these up if you really want to get to the granularity. So Rapid Spanning Tree Protocol, RSTP, which is 802.1W, is essentially an evolution of Spanning Tree Protocol that provides faster convergence than Spanning Tree Protocol could do. So it's rapid because it converges a lot faster. Rapid PVST plus, that's the enhancement of Rapid Spanning Tree Protocol that uses the per VLAN Spanning Tree Protocol as well, and provides a separate instance of 802.1W per VLAN. So each separate instance supports portfast, BBTU guard, BBTU filter, root guard, and loop guard, which we'll talk about later, I think. So rapid PVST is rapid STP combined with the PVST plus. Multiple Spanning Tree Protocol, MSTP, that's an IEEE standard inspired by the earlier Cisco proprietary Multiple Instance Spanning Tree Protocol, which was MISTP implementation. So MSTP essentially maps multiple VLANs into the same spanning tree instance. That's kind of like a per VLAN. So it's you have one spanning tree instance, but you have multiple VLANs running within it. So so for one instance of spanning tree, you can cater for multiple VLANs essentially. So multiple spanning tree, that's the Cisco implementation of the multiple spanning tree protocol, and that provides up to 16 instances of rapid spanning tree protocol and combines many VLANs with the same physical and logical topology into a common rapid spanning tree protocol instance. Each instance supports portfast, BDPU guard, BDPU filter, root guard, and loop guard. So there's been lots of work in the spanning tree protocol essentially. So rapid spanning tree protocol concepts then. So RSTP, which is the IEEE 802.1W, essentially supersedes the original 802.1D. So remember with IEEE, when they increase the letters go up or go along the alphabet, then it's a revision to the original protocols. So while retaining backwards compatibility, so 802.1D devices will work in 802.1W environments, essentially. So the 802.1W STP terminology remains primarily the same as the original IEEE 802.1D spanning tree protocol terminology. So most parameters have been essentially left unchanged. Users that are familiar with the original spanning tree protocol standard can easily configure rapid spanning tree protocol. The same spanning tree algorithm is used for both STP and rapid spanning tree protocol to determine port roles and topology. So RSTP increases the speed of the recalculation of the spanning tree when the layer 2 network topology changes. So RSTP can achieve actually much faster convergence in a properly configured network, sometimes as little as a few hundred milliseconds. So it's really, really fast, hence the term of rapid, I suppose. So if a port is configured to an alternate port, remember alternate port is the new terminology for a non-designated port, it can immediately change to a forwarding state without waiting for the network to converge. And that's really important in terms of keeping traffic going. So if your redundancy needs to come into place, if a link goes down, you want your spanning tree protocol, rapid spanning tree protocol in this case, to quickly move over to those redundant links and keep the network traffic moving. So if you can do that before you've got convergence, then that's better. So rapid PVST plus is a Cisco implementation of rapid spanning tree protocol on a per VLAN basis, with rapid per VLAN spanning tree plus as an independent instance of rapid spanning tree protocol running for each VLAN within your network. So in rapid spanning tree protocol port states and port roles, there are essentially only 3 port states. So in rapid spanning tree protocol, that essentially corresponds to the 3 possible operational states in spanning tree protocol original. So the 802.1D disabled blocking and listening states are essentially being merged into a unique 802.1W discarding state. So what was previously determined as disabled, blocking and listening, is now just simply one state of this discarding role. We still have learning, we still have forwarding. So root ports and designated ports are the same for both spanning tree protocol and rapid spanning tree protocol. However, there are two rapid spanning tree protocol port roles that correspond to the blocking state of spanning tree protocol. So in spanning tree protocol, a blocked port is defined as not being the designated or root port. Rapid spanning tree protocol has two port roles for that particular purpose. So we used to have this thing called the block port, the non-designated port, but now in rapid spanning tree protocol we talk about a backup port and the alternate port. So they've defined that block port a little bit more in a sort of kind of granular way when talking about root ports and designated ports. So we still talk about root port, designated ports, but rather than just a block port, we now talk about backup and alternate. So rapid spanning tree port states and port roles then. So the alternate port has an alternate path to the root bridge. The backup port is a backup to a shared medium such as a hub. A backup port is essentially less common because, well, we now consider hubs to be really legacy devices. So this use of the backup port is really to cater for legacy devices. And we can see in the diagram here, we have our designated ports, we have our root ports, and we have this little backup port between the designated port to a hub and then back again. So that would be a loop within the network. So we can't allow that. So, but it is to only a legacy device, the hub there. So we consider that to be the backup port. And again, it's in that blocking state. So in our STP, as opposed to STP, we use this term rather than just saying it's block port. We now have the alternate port and the backup port. So the alternate port is used within the root bridge, but the backup port is used when we're considering legacy devices. So port fast and the bridge protocol data unit guard, BBTU guard. So when a device is connected to a switch port or when a switch powers up, the switch port goes through both the listening and learning states. So each time it waits for the forward delay timer to expire. So we have a delay of about 15 seconds for each state for a total of 30 seconds, so each end, so 30 seconds overall. And that can present a problem for DHCP, so Dynamic Host Configuration Protocol clients, trying to essentially discover DHCP server because the DHCP process may time out. Okay, so while it's still learning and listening on that particular port, it's not doing any forwarding essentially. So if you're getting DHCP requests from clients looking for servers, they may not be getting through, and it might cause the DHCP process to essentially time out. So we've got this 30-second window. So the result is that an IP version client may not receive a valid IP version 4 address. So when a switch port is configured with port fast, the port will transition from blocking to forwarding state immediately, avoiding that 30-second delay. So you can use port fast on access ports to allow devices connected to these ports to access the network immediately. So port fast should only be used on access ports. If you enable port fast on port connecting to another switch, you risk creating a spanning tree loop. Okay, so port fast is essentially disabling that whole learning and listening discovery phase. Okay, so you only really want it on endpoint access ports, so the ports that connect to clients, for example, for host devices. You don't want want port fast activated on your trunk links, in links, your redundant links within between switches. Never do that. So port fast only on the access ports. So port fast enabled on a switch port should never receive any of the bridge protocol data units, because that would indicate that the switch is connected to the port, so potentially causing a spanning tree loop. So yeah, so access ports never going to be used for any interconnections between switches, hence why you can do port fast on them. Cisco switches support a feature called BPDU guard. So when that's enabled, it immediately puts the switch port into an error disabled state upon receipt of any BPDU. So that protects against any potential loops by effectively shutting down the port. the administrator must manually put the interface back into service. So yes, so this not only protects against any errors occurring, but it also means that it's going to protect in case you try to send BPDUs. So sending BPDUs is a way of trying to infiltrate a network or tamper a network in some way. If you put the BPDU guard on your again your access port, it means that nobody can send manipulated BPDUs onto your network. So from a security point of view, Portfast and BPDU guard are kind of really important to protect your access into that network from the access links. So these are security features that you should add. So alternatives to the spanning tree protocol then. So over the years, organizations required greater resilience and availability in the local area networks. So Ethernet LANs went from a few interconnected switches connected to a single router to a sophisticated hierarchical network design, including access, distribution, and core layers. So that access, distribution, and core design is kind of fundamental to the Cisco approach. Depending on the implementation, layer 2 may include not only the access layer but also the distribution or even the core layers. So these designs may include hundreds of switches with hundreds or even thousands of VLANs, and spanning tree protocol is adapted to the added redundancy and complexity with enhancements such as rapid spanning tree protocol and the multiple spanning tree protocol. So an important aspect to a network design is fast and predictable convergence when there is a failure or change in that topology. Spanning tree does not offer the same efficiencies and predictabilities provided by routing protocols at layer 3. Layer 3 routing allows for redundant paths and loops in the topology without blocking ports. For this reason, some environments are transitioning to layer 3 everywhere except where devices connect to the access layer switch, or in other words, the connections between access layer switches and distribution switches, which would be layer 3 instead of layer 2. So this is the advent of like multi-layer switches. So as we're now seeing networks develop and we're seeing the use of those networks developing, we are essentially having to look at using more refined control. So layer 3 devices definitely have much more control and power and CPU processing assigned to them. Layer 2 devices, although they are managed switches, are fairly smart, they're not able to kind of work out so much stuff. So in more complex the network's getting, the more we're starting to rely essentially on layer 3 than perhaps layer 2, because we're able to control things a little bit more and provide that kind of processing to them. So what did we learn? What did we cover in this chapter then? So so we looked at redundant parts in a switched Ethernet network that may be caused by both physical and logical layer 2 loops. A layer 2 loop can result in MAC address table instability, link saturation, and high CPU utilization on switches and end devices, which can result in the network becoming unstable. That's the problem SDP is trying to sort out. Spanning tree protocol is essentially a loop prevention network protocol that allows for redundancy while creating a loop-free layer 2 topology. So without the spanning tree protocol, layer 2 loops can form, causing broadcast, multicast, and unknown unicast frames to loop endlessly, bringing down a network. So using the spanning tree algorithm, spanning tree protocol builds a loop-free topology in a 4-step process: electing the root bridge, electing the root ports, electing designated ports, and electing alternate or what was blocked ports. During spanning tree algorithm and spanning tree protocol functions, switches use BPDUs, which is known as bridge protocol data units, to share information about themselves and their connections. Bridge protocol data units are used to elect the root bridge, root ports, designated ports, and alternate ports. When the root bridge has been elected for a given spanning tree instance, the spanning tree algorithm determines the best paths to the root bridge from all destinations in the broadcast domain. The path information, known as the internal root path cost, is determined by the sum of all the individual port costs along the path from the switch to the root bridge. After the root bridge has been determined, the spanning tree algorithm selects the root port. The root port is the port closest to the root bridge in terms of overall cost, which is called the internal root path cost. After each switch selects a root port, switches all select designated ports. The designated port is a port on a segment with two switches that has the internal root path cost to the root bridge. If a port is not a root port or a designated port, then it becomes an alternate or backup port. So the backup, don't forget, was for legacy equipment like hubs, mainly alternate ports. Alternate ports and backup ports are discarding or blocking state to essentially prevent loops. So those are the ones that are blocked to not allow frames through. When a switch has multiple equal cost paths to a root bridge, the switch will determine a port using the following criteria. So it's the lowest sender bridge ID, then the lowest sender port priority, and finally the lowest sender port ID. So those are the three criteria that are used to break any deadlocks. Spanning tree protocol convergence requires three timers. We've got the hello timer, the forward delay timer, and the max age timer. So port states are blocking, listening, learning, forwarding, and disabled. In per VLAN spanning tree versions of spanning tree protocol, there is a root bridge elected for each spanning tree instance, which makes it possible to have different root bridges for different sets of VLANs. Spanning tree protocol is often used to refer to the various implementations of spanning tree, such as RSTP and MSTP. Rapid spanning tree protocol is an evolution of spanning tree protocol that provides faster convergence than spanning tree protocol. And rapid spanning tree protocol port states are learning, forwarding, and discarding. Per VLAN spanning tree plus is a Cisco enhancement of spanning tree protocol and provides a separate spanning tree instance for each VLAN configured in the network. Per VLAN spanning tree plus supports port fast, uplink fast, backbone fast, BPDU guard, BPDU filter, root guard, and loop guard. Cisco switches running iOS 15 and upwards run PSVT by default. Rapid PVST plus, Rapid per VLAN spanning tree plus, is a Cisco enhancement of rapid spanning tree protocol that uses PVST plus and provides a separate instance of the 802.1w per VLAN. When a switch port is configured with port fast, that port transitions from blocking to forwarding state immediately, bypassing the STP listening and learning states and avoiding a 30-second delay. You should use port fast on access ports to allow devices connected to these ports, such as HTTP clients, to access the network immediately rather than waiting for the spanning tree protocol to converge on each VLAN. Cisco switches support a feature called BPDU guard, which immediately puts the switch into switch port into an error disabled state upon receipt of any BPDU to protect against potential loops. As well as protecting against potential loops, it just protects for security of the device overall. Over the years, Ethernet LANs went from a few interconnected switches that were connected to a single router to a sophisticated hierarchical network design. Depending on the implementation, layer 2 may include not only the access layer, but also the distribution or even the core layers. These designs may include hundreds of switches with hundreds or even thousands of VLANs implemented amongst them. So spanning tree protocol is adapted to the added redundancy and complexity with enhancements such as part of rapid spanning tree protocol and multiple spanning tree protocol. Layer 3 routing allows for redundant paths and loops in the topology without the need for blocking ports. For this reason, some environments are transitioning to layer 3 everywhere except where devices connect to the access layer switch. So essentially distribution now is moving to multi-layer switches, layer 3 protocols being used within what were essentially switching layers for distribution, and you're now only seeing layer 2 existing for the access layer switches. So it's just the way that the world is developing over time now. So we introduced quite a lot of different terms. So it's just useful to have this list here. I'll let you ponder that. That's in the slide. So just to kind of ponder some of these terms, make sure you're familiar with these things for the next TCA and so on. So thank you for listening. Hopefully there's quite a lot of stuff within spanning tree protocol. It is a rather complex protocol to explain and walk through. It does require a bit of thinking about. Make sure you do the packet tracer exercise. It's really useful to understand that, or help you understand your spanning tree protocol. It is a little bit tricky one to get your head around, but from a network administration point of view, it's obviously a crucial one because every network that has redundancy, which is all of them, will require its use. So a vital protocol.